Good day, this is Professor Will, CBMD PhD. Today is Saturday, April 4th, 2020. It is 8:59 and 40 seconds a.m. Eastern Standard Time, and this is my continuation on cosmology. So let's get started here. According to the usual system of coordinates, called the Schwarzschild coordinates, you cross the horizon when the time coordinate t is infinity. So in these coordinates, it really does take you infinite time to cross the horizon. But the reason for that is the Schwarzschild coordinates provide a highly distorted view of what's going on near the horizon. In fact, right at the horizon, the coordinates are infinitely distorted, or to use the standard terminology, singular. If you choose to use coordinates that are not singular near the horizon, then you find that the time when you cross the horizon is indeed finite. But the time when Penelope sees you cross the horizon is infinite. It took the radiation an infinite amount of time to reach her. In fact, though you are allowed to use either coordinate system, and so both explanations are valid, they are just different ways of saying the same thing. In practice, you will actually become invisible to the Penelope before too much time has passed. For one thing, light is redshifted to longer wavelengths as it rises away from the black hole. So if you are emitting visible light at some particular wavelength, Penelope will see light at some longer wavelength. Wavelengths get longer and longer as you get closer to the horizon. Eventually it won't be visible light at all. It will be infrared radiation, then radio wave. At some point the wavelengths will be so long that she'll be unable to observe them. Furthermore, remember that light is emitted in individual packets called photons. Suppose you are emitting photons as you fall past the horizon. At some point, you will emit your last photon before you cross the horizon. That photon will reach Penelope at some finite time, typically less than an hour for that million solar mass black hole. And after that, she'll never be able to see you again. After all, none of the photons you emit after you cross the horizon will ever get to her. If a black hole existed, would it suck up the matter in the universe? Heck no. A black hole has a horizon, which means a region from which you can't escape. If you cross the horizon, you are doomed to eventually hit the singularity. But as long as you stay outside the horizon, you can't avoid getting sucked in. In fact, to someone well outside of the horizon, the gravitational field surrounding a black hole is no different from the field surrounding any other object of the same mass. In other words, a one solar mass black hole is no better than any other one solar mass object, such as, for example, the sun that's sucking in distant objects. What if the sun became a black hole? Well, first let me assure you that the sun has no intention of doing any such thing. Only stars that weigh considerably more than the sun, and their lives as black holes. The sun is going to stay roughly the way it is for another 5 billion years or so. Then it will go through a brief phase as a red giant star, during which time it will expand to engulf the planets Mercury and Venus, and make life quite uncomfortable on Earth, oceans boiling, atmosphere escaping, that sort of thing. After that, the sun will end its life by becoming a boring white dwarf. If I were you, I'd make plans to move somewhere far away before any of this happened. I also wouldn't buy any of those 8 billion year government bonds. But I digress. What if the sun did become a black hole for some reason? The main effect is that it would get very dark and very cold around here. The Earth and the other planets would not get sucked into the black hole. They would keep on orbiting in exactly the same paths they follow right now. Why? Because the horizon of this black hole would be very small, only about 3 kilometers. And as we observed, as long as you stay well outside the horizon, the black hole's gravity is no stronger than that of any other object of the same mass. Is there any evidence that black holes exist? Yes. You can't see a black hole directly, of course, since light can't get past the horizon. That means that we have to rely on indirect evidence that black holes exist. Suppose you have found a region of space where you think there might be a black hole. How can you check whether there is one or not? The first thing you'd like to do is measure how much mass there is in that region. If you found a large mass concentrated in a small volume, and if the mass is dark, then it is a good guess that there's a black hole there. There are two kinds of systems in which astronomers have found such compact, massive dark objects. The centers of galaxies, including perhaps our own Milky Way galaxy, and X-ray emitting binary systems in our own galaxy. In appearance in the 1995 edition of Annual Reviews of Astronomy and Astrophysics, 8 galaxies have been observed to contain such massive dark objects in their center. The masses of the cores of these galaxies range from 1 million to several million times the mass of the Sun. The mass is measured by observing the speed with which stars and gas orbit around the center of the galaxy. The faster the orbital speeds, the stronger the gravitational force required to hold the stars and gas in their orbits. This is the most common way to measure masses in astronomy. For example, we measure the mass of the Sun by observing how fast the planets orbit it. And we measure the amount of dark matter in galaxies by measuring how fast things orbit at the edge of the galaxy. These massive dark objects in galactic centers are thought to be black holes for at least two reasons. First, it is hard to think of anything else they could be. They are too dense and dark to be stars or clusters of stars. Second, the only promising theory to explain the enigmatic objects, known as quasars in active galaxies, postulates that such galaxies have supermassive black holes at their core. If this theory is correct, then a large fraction of galaxies, all the ones that are now or used to be active galaxies, must have supermassive black holes at the center. Taken together, these arguments strongly suggest that the cores of these galaxies contain black holes, but they do not constitute absolute proof. Two very recent discoveries have been made that strongly support the hypothesis that these systems do indeed contain black holes. First, a nearby active galaxy was found to have a water maser system, a very powerful source of microwave radiation, near its nucleus. Using the technique of very long baseline interferometry, a group of researchers was able to map the velocity distribution of the gas with very fine resolution. In fact, they were able to measure the velocity within less than a half a light year of the center of the galaxy. From this measurement, they can conclude that the massive object at the center of the galaxy is less than half a light year in radius. It is hard to imagine anything other than a black hole that could have such mass concentrated in such a small volume. Good day, this is Professor Will, CBMD PhD on Cosmology and Astrophysics. Hope you enjoyed listening and have a great day.